Okay, so for part B, we have a man standing on the ramp and he begins to climb the ramp. So I'll draw my man here. So initially he's at O, position O, and over time he starts to move up the ramp. Now, key thing to note, when he's at O, what force does he bring into the picture? Well, he has his weight, right? And this is his weight. And if we draw the line of action of the force, it will just be a vertical line, right? And this line of action of the force happens to cut through the pivot exactly, so we know that perpendicular distance equals to 0. Now, when this man starts to move up, you realize that, for example, if he reaches here the center, his weight is still the same, it acts downwards. However, this time the perpendicular distance from the pivot to the line of action of the force has increased. In this case, it's 120 cm. And if he moves up further, the perpendicular distance will increase again, right? Because line of action of force is here. Perpendicular distance will this time be all the way here, which is 240 cm. So we know that his perpendicular distance is increasing. Now, so what? We know that moments equals to force times perpendicular distance, right? And force is the same because it is his weight, but perpendicular distance has increased as he climbs up the ramp. So therefore moments will increase. Okay, so this is the key idea that is behind this question, but it's 3 marks, so I'll just give you a hint of how to solve it. So you must mention that at O, his perpendicular distance is 0 because that's a very special case, and therefore what is the clockwise moments caused by him? And as he moves up, what happened to perpendicular distance, and therefore what happens to the clockwise moments that he creates as he goes up. Alright? Now for part 2, we have to suggest a point at which another force must act on the ramp. So this beam over here is in equilibrium, right? So 2 conditions must be met. Number 1, all your net force, there should be 0 net force, right? So here I'm going to relabel all the forces so we can take note of them. But before that, let me erase the man away. Okay, so we have 3 forces in the diagram, right? And over here we are asked to point out another place where the force must act on the ramp. So here we have a vertical force. Now this vertical force, we know that net force must be 0, right? So this vertical force can be balanced out by another vertical force, which is due to the weight of the beam. However, here we have a horizontal force at T, and it's acting to the left. Now, if we have no more forces, this will never be balanced. There will be net force. Then the beam cannot be in equilibrium, right? So we need a horizontal force that at least acts in the opposite direction. Okay, or it has some component that acts in the opposite direction, right? And that force can only come from this point over here, O. Okay, now part 3, by considering moments about the top T of the ramp, explain why this other force is necessary. So for part 2, I used the fact that there is no resultant force or no net force. But for part 3, we are supposed to use moments, and we take the pivot to be T. So this is our new pivot at T. So once we choose the pivot to be T, we realize that these 2 forces, because they are acting directly on T, the perpendicular distance will be 0. That means the moments caused by these 2 forces can be neglected. So when we consider T, we just have to consider this force and the moments it creates. In this case, the moments it creates will be no longer clockwise, but it will be anti-clockwise. And hence, there needs to be another force to counteract this anti-clockwise force, right? And that force, we know, happens to be at O, as mentioned earlier, right? But this force must somehow create a clockwise moments about T in order to balance out this force. Alright, so with that we have covered all the questions.